This next learning goal, 1.3, having to do with atomic sizes and ion sizes, is conceptually difficult for some people. So what we're going to do in this video is just discuss the basics and breaking it down to the three different comparisons. And those comparisons are, one, if we're looking at two elements horizontally, so boron versus carbon. The other is if we're looking at two elements vertically. We could say like oxygen versus sulfur. And then the other is if we're looking at two ions of an element. So we could say like Br and Br minus, the plus and minus version of that. And then we could say like Mg and the neutral and minus version of that, and the neutral and 2 plus version of that. So we could look at these different situations. And it really boils down to this idea of ionization energy. And ionization energy is simply how hard the protons in the nucleus pull on the electrons. Said differently, we could think of it as how hard it is to remove an electron. But what's causing it to be pulled in are those protons in the nucleus. So if we have an element here, and we think of this here as the nucleus, and we think of this here as the electrons, we have a force pulling in on that, and that's the ionization energy. Okay. So what's going to make that force greater? Well, there's a couple things that can make that force greater. That force is greater when this electron is closer to the nucleus, and that force is greater when this charge value is greater. Okay. So if we look at that horizontal relationship we were talking about here between boron and carbon, okay, so we have boron and carbon, and we're going to draw both of those. Okay, so let's draw boron, okay, and then let's draw carbon. So we have a horizontal relationship, and when you're dealing with a horizontal relationship, it's always about the protons in the nucleus, or the nuclear charge. So let's first just identify what's going on in the nucleus. Boron has 5 plus things, 5 protons in the nucleus, and carbon has 6 plus things in the nucleus. Okay. Now, in terms of electrons, the best way to think about this is that boron is not pulling on 5 electrons. Boron is pulling on 5 electrons, which are in the second energy level, and we're going to think of those as rings. Okay, so there's the first ring, and then here is the second ring, and that's because boron is in that second period on the periodic table. All right, now carbon has also 2 rings, but carbon has 6 protons pulling on those 2 rings. So those rings are going to be pulled in tighter. Okay, so in terms of size, boron is a larger atom because it has a smaller ionization energy. Carbon is a smaller atom because it has a larger ionization energy. And it has a larger ionization energy because it has 6 protons pulling on those 2 energy levels, whereas boron has 5 protons pulling on those energy levels. Let's look at oxygen versus sulfur in this case. Okay, so I'm going to draw this one, just same place as I did it before. Oxygen, sulfur. Okay, let's do the same thing here. Oxygen, we know, has 8 positive things in the nucleus, and it's got 2 energy levels. So let's go ahead and look at that. 1, 2. Now, sulfur has 16 protons in the nucleus, but don't get fooled by that. It's got 3 energy levels. Okay. And the third energy level adds what we call a shielding effect, meaning that these negatively charged energy levels, this one right here and this one right here, are shielding the nucleus that's trying to pull on that outer valence shell. So because of that, oxygen has a higher ionization energy. Its 8 protons can pull harder on its valence electrons, thus it's smaller. Conversely, we could say that sulfur has a lower ionization energy. The 16 protons do not pull as hard because of the shielding effect. Thus, it is a larger atom. So we have this inverse relationship between ionization energy and atomic size. It's it's important to understand that when you're looking horizontally, it's about the protons in the nucleus. That is the effect because we're controlling for the energy levels. And when we're looking vertically, okay, whereas high ionization energy is going to be over here, high ionization energy is going to be up here if you're looking vertically. When you're looking vertically, it's about the number of energy levels. So protons, horizontal, shielding, vertical. Now let's look at that other circumstance we were talking about having to do with like chlorine. Okay, so let's take a look at chlorine in its neutral form and chlorine in its negative form. And to do this, I found the best thing to do is just to draw out the number of protons and the number of electrons. So chlorine has 17 protons in its neutral form, and it's got 17 protons in its negative form. In its neutral form, it's got 17 electrons, and in its negative form, it's got 18 electrons. So if you notice here, chlorine, its protons are pulling on 17 electrons here, okay? But here, the 17 protons are pulling on more electrons. They're having to work harder over here. So what's going to happen is chlorine in its neutral form is going to have a higher ionization energy, and it's going to be smaller. Chlorine in its negative form is going to have a lower ionization energy, and it's going to be a little bit bigger. Notice 17 has a harder time pulling on 18, so they're more scattered. Let's look at another situation. Let's look at that magnesium situation. You have magnesium 0, magnesium 2+, P+, E negative. Okay, magnesium is going to have 12 protons in both forms. That's what makes it magnesium. Here it's going to have 12 electrons, and here it's going to have 10 electrons, okay? So in which cases does it have to work harder? Well, in this case, it's got to work harder here. Let's look at why. 12 protons pulling on 12 electrons. That was the higher ionization energy case before, but we were comparing it to a situation in which those 17 protons in chlorine were pulling on even more electrons. Here, when we're comparing these 12 protons have a harder time pulling on those 12 electrons than these 12 protons pulling on those 10 electrons. So when you're positive, you're going to be smaller than your neutral counterpoint. And when you're negative, you're going to be larger. But again, it boils down to the protons pulling. So, horizontal, protons. Vertical, shielding. And when we're looking at ions, just compare the proton to electron ratio. Whoever has a greater proton to electron ratio is going to be smaller and have the higher ionization energy.